So let's take a look at our calendar. Today is February 29th. Happy Leap Day. Today we're going to talk about lesson 11, solving systems by algebraic methods. This is kind of a funny class. I do have quests to give back. We had our quest last class. I will give it back during this class. But it's kind of funny because we had that snow day and then the quest and we rescheduled stuff. And I think from what I've seen, everybody so far is kind of on track dealing with lesson 10 on their own. I made that video. Did anybody happen to go to my colleague's class on Friday? It was probably difficult scheduling wise for most of us. But anyway, there's a video there solving systems of equations in a nutshell. If you graph two lines and you were looking for the solution to the system, where are you going to find it? The intersecting point. That was the heart of lesson number 10. So you want to solve a system of two equations, you graph your two lines, you estimate the point of intersection. Now, there are some downsides to solving systems of equations graphically. Number one, do you get it right every time when you know? And in fact, if you watched my video, what did you find? I made a mistake on one of them, right? There was some books and CDs thing, and I think I said 4 books and 8 CDs, and it should have been 5 and 7. And just as soon as you start drawing things on your graph paper, you're going to be wrong. And so you make your best guess, but it's not 100% accurate. The other thing is graphing takes a long time. It's just a time-consuming process. So today we're going to talk about solving the same kinds of systems, same kinds of problems as lesson 10, but we're going to use algebra to solve them. And it has 2 advantages. Number one, it is probably a little bit quicker than drawing lots of lines. Number 2, more importantly, it is 100% accurate. As long as you do things correctly, you will get the exact right answer, and you'll never run into the problem that I did on the video where you're close, but not quite right. That said, when we take our next test, you can be close and not quite right and still get full credit because I know that you're going to be, you're drawing things. And so those are all approximations. All right. So here at the top of page 87, we're just going to kind of jump around a little bit. We're going to talk about 2 techniques. One of them is called substitution. One of them is called elimination. We're going to use substitution first to solve this particular system of equations right here. Now, the fact is, I've already typed up the entire solution to this problem. It is right there in front of you, but I want us to feel like we're doing something and not just reading what I have typed up. So if you go all the way to the back of this packet, you will find a blank page, just the very last page on the back. Can you go to that blank page? I've got a blank page here. Can you just recopy the system here? And we'll solve it from scratch. Basically, we're just looking for a place that we can do some work. Okay, step 1 for solving a system of equations using this new technique called substitution is to solve one of those equations for one of those letters. You got a lot of choices there. You could solve the first equation for x, you could solve the first equation for y, you could solve the second equation for x, you could solve the second equation for y. 4 options. Sometimes one of those options is much, much better than the others. And so I'm going to write something down that I ask you not to copy because I'm going to make a bad choice first, and then we'll make the best choice possible. So don't copy this. Suppose that we decided we were going to solve this equation for x. First thing I need to do is move the negative 2y away by adding it to both sides. So we get 6x equals negative 3 plus 2y. Don't copy this, right? Add the 2y over to the other side. And now to solve for x, what do we do? Divide both sides by 6. So divide by 6, divide by 6. And we get x equals negative 3 plus 2y over 6. It's fine, it's correct. We'll get the right answer as long as we do the process correctly from this point on. But that involves a fraction. And everything that we do from this point forward is going to involve a fraction because we're starting the problem with a fraction. So potentially, if you can avoid introducing fractions by making a different choice, then I'd encourage you to do so. The reason this one had fractions was because of that 6 in front of the x, right? Maybe we could see ahead of time. Because of that 6, we're going to have to divide by 6 in the last step. To solve the first equation for y, what will you need to divide by at the end? The negative 2 fractions. To solve the second equation for x, what will you have to divide by? 4 fractions. To solve the second equation for y, what you have to divide by? 1. No fractions. That's the winner. And so if you are fortunate enough to have an equation where one of these letters has an invisible 1 in front of it, you grab that one because all of the other choices will involve fractions. So please do copy this down. We're going to solve this equation for y. What's that? Well, you'll see the entire process. It doesn't. I can't answer that at the moment, but once we finish the problem, you'll see why we're only choosing one. Okay, to solve for y, we need to move the 4x over to the other side by subtracting 4x from both sides. So the left-hand side is simply y. The right-hand side, 5 minus 4x. Everybody buy it? Subtract 4x from both sides. By making that choice, what have we avoided? Fractions. Fantastic. If there were not a 1 in front of that y, then you couldn't avoid fractions to do substitution. And in fact, I would choose a different technique entirely, not this one, if there weren't a 1 in front of one of these variables. We'll see the other technique today. Okay, you solve one equation for one variable. We've done that. Step 2 is to plug that thing in to the other equation. So what we just have here is an expression that is equivalent to y. All of this stuff is exactly the same as y. It is interchangeable with y. So we're going to go to the other equation and we're going to swap out the y for the stuff that is exactly equal to y. So here we go. This equation now becomes, I'm copying everything, I'm just making one small change. 6x minus 2 times. And now I'm up to the part with the y, and I'm changing the y for something that is identical to y. What is equal to y? 5 minus 4x equals copying the negative 3. Needs to be in parentheses. We're going to get it wrong the way we've currently written it here. So we'll highlight, we made the one small change. All of that stuff got substituted for y, but as Evan points out, we need parentheses because y used to be written as a single thing, y. Now it is written as 2 terms, 5 minus 4x. And that negative 2 sitting in the front of y needs to be sitting in the front of all of y, and we're going to need to distribute that. Parentheses are mandatory here. Solving the rest of this is going to be pretty straightforward, but does everybody buy the logic of why this is an okay thing to do? Like, I don't want it to just be a memorized procedure. It's like you solve one variable, solve one equation for one variable, and then you substitute it into the other. Totally legal, because all you're doing is trading one thing for its equal. Okay, so let's finish here. 6x, now we'll distribute that minus 2, so what do we get? Negative 10. Yeah, make sure you catch that change of sign, right? Let's say plus 8x minus 2 times minus 4x equals negative 3. And now the equation is going to look friendlier and friendlier as we go. By the way, the reason this equation is something nicer than either of the first two, how many variables are in the first equation? 2, x and y, right? How many in the second equation? 2, x and y. How many in the equation we solved for? Also 2, x and y. But then when we did this substitution step, how many? Just 1. That was the goal. I can solve an equation if it's got just lots of x's in it. Jesse, you all right? Okay, now we'll combine like terms, right? 6x plus 8x, that's 14x. Copy the minus 10 equals negative 3. Add the 10 to the other side. 14x equals 7. Divide both sides by 14. So x equals 7 over 14. Make sure you always reduce your fractions in this class. X equals 1/2. Okay, so we've got our x. Oftentimes when you have x, you're done with the math problem. Not here. What do we also need to find? We need to find y. Remember back to lesson 10, you graph 2 lines, you find a point of intersection. How many numbers are associated with that single point? 2. There's an x and a y, right? We just found the x. We also have to find the y. The best place to go to find the y is the very first equation where you solve for one of the letters. So let's plug this 1/2 in for x in that equation. So it says y equals 5 minus 4x, but instead of x, what did we discover? 1/2. So there you go. 5 minus 4 times 1/2 is 2. 5 minus 2 is 3. So that means that our solution is either, you can write it as an ordered pair, like an x and a y. Make sure you put them in the right order, 1/2, comma 3. Or you can just write it out, x is 1/2 and y is 3. Questions on substitution? It's called substitution because you substitute in that first equation. We substituted instead of y, we put 5 minus 4x. Okay, so all the steps are written out back on the page that we left. So if you need a kind of a reminder, you can just read through this. It's in English, but we're not going to read through it here. I do want to point out, so we're back on page 87 now. Let's go back to 87. I do want to point out that we can check our answer. We've discovered that it was 1/2 and 3, and we can make sure that that really is the solution to the system. What that would mean is taking x is 1/2 and y equals 3, plugging those guys in for x and y in both equations, and you better find out that both equations lead to true statements, right? And so in this first equation, you change x to 1/2 and y to 3, and that's written here at the bottom of the page. X becomes 1/2. X becomes 1/2, y becomes 3. 6 times 1/2 is 3, that's there. 2 times 3 is 6, that's there. How much is 3 minus 6? Oh good, it's -3, just like it was supposed to be. And you can check the other equation too. Plug in 1/2 and 3 for x and y. Make sure that it's true. It's not mandatory. I won't require you to do it on a test. As long as you do everything right, they will work, guaranteed. But it's something that if you want to make sure that you haven't made any errors, you could always check. Okay, on the next page, we are going to see the other technique. This thing is going to be called the elimination method or the addition subtraction method. We'll see why those are good names for this method in a moment. So this technique, this method, solves exactly the same kinds of problems. We're just giving you different ways to solve exactly the same kinds of problems. 2 equations with 2 unknowns. That's what we're after. Okay, let's take a look at this problem here in number 3. 9x plus 6y equals 5. 6x minus 5y equals 9. What about those equations suggest that substitution is going to involve fractions if we did the substitution method? Yeah. Every variable has something on it, right? We were looking for an invisible 1 in front of the x or the y any place, and we don't have it. So no matter what letter we solve for in either equation, you're going to have to divide, which means fractions, which is fine. Substitution method still works. But here's an alternative. And this method will completely avoid fractions until the very end of the problem, which is great. Okay, so forget those 2 equations at the moment and just jump down to these equations right here. Don't worry about how we got here, but just focus on those for a second. Suppose that I added these 2 equations together, just going straight down. If you add, for example, 12y plus 15y, what do you get? 27y, that's there. If you add 10 plus -27, what do you get? -17, that's there. If you add 18x plus -18x, what do you get? Nothing. And so adding these 2 equations, just going straight down, gives us the equation 27y equals -17, which has how many variables in it? Just 1, which is great because we can solve that. So if by some miracle you can make it so that in front of one letter is a number, and in front of that letter in the other equation is the same number but the opposite sign, 18 and -18, you can add them up and that variable just disappears, right? We see what makes this work, building an 18 and a -18. Okay, so let's go back to the original set of equations. Back up here. The question is, can we multiply this thing by something to turn it into an 18? Because that was a great thing to have at the end. What can you multiply by? 2, right? Let's multiply everything by 2. You can't just multiply one side of an equation by 2. So really, it's down here. There's the equation in its original form, times 2, everything times 2. So how much is the 2 times 9x? 18x, that's good. 2 times 6y, that's the 12y. 2 times 5 is a 10. It's really easy to forget to multiply the 5, but you got to multiply everything by 2. Good question. We'll come to that. Okay, look at the second equation. What can you multiply this by to turn it into 18? 3. I actually really want it to be negative 18 to make it easy for me to just add the equation. So what can you multiply by to make negative 18? Negative 3. So we're going to multiply everything in that second equation by negative 3. Let's make sure that I've typed it correctly here. That's negative 18x. What's the next one? Negative 15y? Positive 15y, right? Careful of your signs. And then here times here. Negative 27, it is right there. Okay? So the last piece of this puzzle is what Evan had asked. Where did the 18 come from? Okay, so what we are after is something that 9 and 6 both go evenly into. Now you could just say 54, you could just multiply them, but if we can get something smaller, that's better for us. What do 9 and 6 both go into? Smallest is 18. We call that the least common multiple. LCM is probably something you've seen in a previous class.
Are you always going to pick X?
No. Well, whatever you want to do is fine. You could do either X or Y. Okay. So coming down here, what's the solution when we divide both sides by 27? Say it as a fraction. Negative 17/27. That's it. That's our final answer. There's the value of y. We avoided fractions, I promised, until the very end. You can't avoid fractions entirely. That's the right answer, and it's a fraction. So you got to have a fraction at some point. We delayed fractions until the very end. That is the correct answer. If you type negative 17/27 into your calculator and you write some decimal approximation on your test, you're going to lose a point because this is the only right answer. And as soon as you stop writing your decimal, you're wrong. Yes? Because the decimal probably goes forever. Now, there are ways to capture like the repeating nature of a decimal. Like if you had a third, you know that's 0.33333 forever, right? So you could put 0.333 ... That captures the repeating nature, and that's a full credit answer. What's the other way to say the 3 repeats? Put a line over it. You could put 0.3 with the bar on top. That's a full credit answer. But if you don't capture the repeating nature of your decimal and you just stop it someplace, that's not a full credit answer because it's not exact. Now, that said, how much is a quarter as a decimal? 0.25. That's exact. That's full credit. So I'm not talking about the ones that terminate. I'm talking about the ones that repeat. So why even bother getting into that game about like, well, does it repeat? Does it terminate? How do I write it correctly? You're done. Like, there's no reason to go any farther to make the problem more work for yourself. The negative 17/27, perfectly acceptable answer. Okay. That's the y. We still have to find the x. So how do we do it? It says find the value of the other variable. All right, so you can substitute. You have 2 equations up here at the top. You can take your negative 17/27 and put it right here, negative 17/27. Or you could put it in the other equation and then solve for x. I want to convince you that that's going to involve a lot of work with fractions. Right? Because first you'd have to multiply the 6 times the negative 17/27. Then you'd have to subtract that to get it over here. We're trying to get the x by itself. And then you'd have to divide everything by 9, which is already a fraction on the right-hand side, which you're now dividing by 9. It's kind of a bear. I mean, you could do it. As long as you are good with your fractions, you're fine. And in fact, up until this semester, that's how I used to teach this. But you guys are my guinea pigs here. We're going to try a new technique that one of my students suggested last semester. Here is the algebra involved in what I just discussed. Lots of fractions by plugging in and moving stuff around. So a technique suggested by one of my students last semester, instead of doing that, is to just say, well, why don't we go back to the original system of equations and eliminate the other variable? We eliminated x and we found y. How about we just start the problem over? Evan said, how do you know you should eliminate x? You can eliminate y if you want to, and that's another alternative here. So take a look at the same two original equations. We already eliminated x. Let's try starting over and eliminating y. So you're going to look at these y values, y terms, and try to decide what do they both go evenly into, looking for the smallest thing possible. What do you think? 6 and negative 5? It's 30. 30 is the winner. You just multiply them, and we can't do any better than that. So let's give it a shot. Turn into 30y and negative 30y, just by looking at those numbers in front of the y's. So you currently have a 6y. What do you multiply it by to turn it into a 30y? It's 5. So you'd multiply everything in this first equation by 5. In the second equation, you have a negative 5y. Trying to turn that into a negative 30y. 6. So you multiply everything here by 6. Just to save some time, we're not going to finish this, but you would distribute, you would add, the y's would disappear because you made them opposites of each other. 30y and negative 30y would just disappear. And you'd have an easy equation with no fractions in it that you would solve for x. Probably x is a fraction, but you've avoided all of the work from up above. I agree. To do it which way? It makes sense to me now, but for years I taught it the hard fraction way. So yeah, I think this is better. Okay, number 4. Usually 2 lines intersect at a single point, which means you got your solution as the point of intersection. But there are 2 special cases that we looked at in our previous lesson. So this is where hopefully you watch the video. So the 2 special cases, how can you make 2 lines not intersect each other? If they're parallel, right? And how many solutions do we have if you have 2 parallel lines? None, because there are no points of intersection, right? There's no point that's on both lines simultaneously, so there's no point that satisfies both equations simultaneously. What's the other special case? Where they're on top of each other, where it's really the same line twice. In this case, how many solutions are there? Infinitely many, right? Because as soon as you pick a point on one line, it is automatically on the other line. Infinitely many points of intersection, right? All of them. Okay, so if you're looking at a picture, it's pretty easy to tell whether you have parallel lines or the same line twice. But we have no pictures here. And so we need to know what to look for in our algebra that's going to say, hey, you're in one of these special cases, even though you can't see the picture. So let's go to the next page. Number 5 says, use substitution to solve each of these systems. Something strange will happen. So let's give it a shot. Okay, we're going to use substitution. Remember, substitution involves you solve one equation for one variable. It's already done, actually. For example, this equation is already solved for y, so great. So y and 2x plus 1 are identical. And then you take that thing and you substitute it into the other equation. So instead of this y, what can we put? 2x plus 1, because that's exactly what y is equal to. So this equation becomes, I'm going to copy the right-hand side first. On the left-hand side, what we just said, instead of y, we're going to put 2x plus 1. Draw kind of an arrow here. This system is so simple that it's kind of easy to get distracted by, well, what's really going on with our substitution? But anyway, that's all we're doing. Substituting 2x plus 1 for the second y. Okay, I see x's on both sides. Let's get them onto the same side by subtracting 2x from both sides. Subtract 2x. Subtract 2x. What is the resulting equation? Nope. 1 equals 3. With a good question. That was the right intonation. 1 equals 3? That's strange. Okay, we'll come back to that. Let's take a look at part B. We'll do substitution again. Which variable would you solve for which equation would you solve for which variable? One of them is already done. Solve the second one for y. Too much work. Which one is already solved for one letter? Is the top equation. It's already solved for y. So all we're going to do is substitute that in to the second equation, right? Okay, so here we go. 6x minus 3 times, and then instead of y, what is the same as y? 2x plus 1 equals, copying the right-hand side, negative 3. I have made a mistake on the board. Do not make that mistake. So correct my mistake on your paper. What's my mistake? Parentheses. Gotta have it. Okay, let's distribute that negative 3. So we go 6x. And distributing the negative 3 first becomes negative 6x. And then distributing the negative 3 is negative 3 equals, right-hand side copied, negative 3. On the left-hand side, combine like terms. What's the resulting equation? Negative 3 equals negative 3, which is true, but also not expected. That's not what we were hoping for. We were hoping we would get something like x equals 5. Instead, we get negative 3 equals negative 3. So here's the punchline. If all the variables disappear, like the x's all disappeared, then you're in one of the special cases. Parallel lines with no solution, same line with infinitely many solutions. If you get a ridiculous equation that is blatantly not true, like 1 equals 3, which one do you think that is suggesting? Parallel. Because 1 equals 3 is not true. And when you have parallel lines, you have no solutions. And so we can, like if 1 equals 3 is going to suggest no solutions or infinitely many things are true, I would suggest no solutions is more reasonable. So 1 equals 3, our conclusion is no solutions. In the My Math Lab homework, I just want to cue you into a symbol that you might not have seen before, but you will see in My Math Lab. You could say that the solution set, the set of all solutions, is empty. There's no solutions, right? And mathematically, there's a symbol for this empty set. It's like a 0 with a diagonal slash through it. So if you see that symbol in My Math Lab, they're talking about no solutions, parallel lines. Jeff? Yes, don't. Yeah, it is a bad habit. Yeah. Okay, coming back down here to the other special case where we got negative 3 equals negative 3. What do you think? No solutions or infinitely many? Infinitely many. Negative 3 equals negative 3 is true all the time. This tells us that there are infinitely many solutions. Same line twice. So, yeah, so if, so the problem here is going to say solve the system. And so you need to tell me about the solutions of the system. And like in lesson 10, we talked about how the graph cues you into what the solutions are, but ultimately the final thing you need to write is about the solutions, not about the graph. Okay, so it's written here, but it just says if the variables all disappear, it's one of two special cases. If you get something ridiculous like 7 equals negative 2, that means no solutions. We use the word inconsistent last class. Empty set is that symbol. If you get something true like 4 equals 4, then there are infinitely many solutions, and we use the word dependent last time. Okay? All right, so before we jump into the activity, just one final word of caution about substitution and elimination. Before that, typically somebody asks me, you know, hey, can I just learn one of these because they both solved exactly the same sets of problems? And the answer is no. On the tests, you are going to see a page where it's going to have two systems of equations, two different ones. And it's going to say on one of these, you get to do substitution. On the other one, you have to do the elimination. And you get to pick. So I'm not going to force you ever to do one or the other, but I am going to force you to do one of each, right? And with some practice, you'll start to see, oh, this kind of system is easier for substitution, and this kind of system is easier for elimination. Yeah. Okay, so the word of caution. If we go back to this one right here, this was the thing we did on the back of the, you don't need to go there now, but this is what we did on the very back page. And I said the technique after we solved one equation for one variable was to do what? Substitute into which equation? The other equation. We didn't really make such a big deal out of it, but we're going to make a big deal out of it now. You have choices, right? You're substituting. Instead of y, you're going to put 5 minus 4x. We used the other equation, but just as well, couldn't we have substituted this y and changed it to a 5 minus 4x? After all, y and 5 minus 4x are interchangeable. They're exactly the same. So don't write this. But if you were to substitute into this equation, it becomes 4x plus something equals 5. What's the something? What is y in this problem? 5 minus 4x. Yeah? Totally legal. All we did was change y into 5 minus 4x. What happens when we combine like terms? 5 equals 5, right? 4x, negative 4x, cancel. All the variables disappeared, and we just got through saying that's our cue that we're in one of our two special cases, parallel or the same line twice. Was this problem one of our special cases? Look at the answer. The answer was how many solutions? 1. X was a half and y was 3. We were in a very normal intersecting lines case. But if you accidentally substitute not into the other equation, but into the same equation, you will always turn it into this special case, where you get something that is true, like 5 equals 5, but not helpful. So you've got to be really careful, because this will always give you the wrong conclusion. It is important to substitute into the other equation. Okay? Okay. All right, activity starts on the next page. Raise the flag if I can help.